Cool. Yeah, thanks for the introduction and thanks everyone for coming. So yes, I'm going to give a talk on the risks and trade-offs of solar geoengineering. And so first I'd like to acknowledge some of my collaborators. So at the Met Office and Exeter, my supervisor, Jim Hayward, and Andy Jones and Mohit Dalvi, and then been working a lot with people in Cornell. So Danielle Visioni, Douglas McMartin, and Walker Lee. So I don't think I need to tell anyone that's listening about the huge gaps that we have in terms of our targets for emission reductions. If we continue on our current path, we're heading for between 2.6 and 2.9 degrees Celsius. And we've decided that 1.5 degrees was the threshold for a safe climate. And there's a huge gap in terms of our emissions in order to get there. And so that is the main motivation for looking at other ways we could intervene on the climate to reduce the risk from climate change. So the various methods that are proposed for solar geoengineering, there are three types. So starting from the bottom, some people talking about brightening marine clouds. So marine clouds are low clouds, so they have a low effect on the long wave radiation. But they are bright clouds that hang above dark ocean surfaces. So if you increase the brightness of these clouds, then that will increase the amount of sunlight that is reflected and cool the planet. The second type is to thin high clouds, high cirrus clouds. So because they're high clouds, they act more on the long wave part of the spectrum. So then that would allow for more heat to escape to space. So it's not technically a form of solar geoengineering, but it's classified with solar geoengineering because of it being a similar technique. And then maybe the more well understood and talked about technique is stratospheric aerosol injection. And that involves deliberately adding aerosols to the stratosphere to reflect more sunlight. And so I'll be focusing on stratospheric aerosol injection in this talk because it's the one that that most people are thinking about these days. So just to give more context on why and how we think of solar geoengineering, I'm gonna show this sort of right now infamous napkin diagram. So on the top, I have emissions of greenhouse gases as a function of time, and the bottom, climate impacts. So it's a very vague term for climate impacts. It's roughly climate impacts will be proportional to surface temperature change. Yeah, there's no sort of defined number for climate impacts, and the time axis is also quite vague. So obviously, if we continue increasing our emissions of greenhouse gases, the climate impacts will continue to increase. So that is definitely not what we want to do. So plan A for now is to reduce greenhouse gas emissions to net zero. And after that point, the temperature change will plateau and the Earth will stop warming, but the global mean surface temperature will roughly stay the same, as will most climate impacts, even though melting glaciers, ice sheets, and rising sea levels lag behind surface temperature change. So they will continue beyond the point where we reach net zero emissions. So the plan now is basically to reach net zero and then continue by removing carbon dioxide, so having sort of negative emissions of greenhouse gases, and then that will bring down the global mean temperature and climate impacts. So then we will reach a maximum in surface temperature change, and then it will decline again. So the idea of how we could use solar geoengineering to reduce climate impacts is to so-called shave this peak in warming by injecting aerosols in the atmosphere. So what does the IPCC say about solar geoengineering? So IPCC has a set of of sentences, and they give levels of confidence around these statements. So they say with high confidence, it could offset some of the effects of greenhouse gases on the climate, including the carbon water cycles. It also says with high confidence that there could be substantial, residual, or overcompensating climate change on regional and seasonal scales. They say that there are large uncertainties around the interactions between aerosols, clouds, and radiation. They say with medium confidence that it could increase land and ocean CO2 sinks, but it wouldn't stop the increase in atmospheric CO2 or ocean acidification. And if it was implemented rapidly, it could abruptly change the water cycle. The sudden termination in a high CO2 scenario would lead to rapid climate change. Yes, because adding aerosols is only a temporary fix that would mask the warming that would be there otherwise. So if we stop adding aerosols, all the warming that is masked would come back very quickly. That is called the termination shock, and it would lead to very rapid warming, and that could be devastating for humans and ecosystems. But the gradual phase out of solar geoengineering, if it's combined with emission reductions and carbon dioxide removal, could avoid these termination effects. So that's basically talking about this peak shaving scenario that I showed earlier. So then I wanted to talk about a few things that we do know about stratospheric aerosol injection from climate modeling studies. So we know that volcanic eruptions that happen in one hemisphere shift the ITCZ and cause large precipitation changes in tropical land areas. So I'm showing a plot from Jim Hayward's paper. On the left is the precipitation change you get from northern hemisphere volcanic eruptions, and on the left, on the right is from southern hemisphere volcanic eruptions. And so you see this shift of the ITCZ towards the cooler hemisphere. Is that right? No, sorry, towards the warmer hemisphere. And so in the case of northern hemisphere eruption, you have a reduction in precipitation in the northern part of Central Africa, but in the southern hemisphere eruption, you have increase in precipitation in the northern part of Central Africa. So basically, these results indicate that if we were to do stratospheric aerosol injection, we wouldn't do it in a single hemisphere, but we would have to balance it between both hemispheres in order to avoid these huge shifts in the ITCZ. The second thing we know from climate modeling studies is that if we compensate for all of the greenhouse warming through solar geoengineering, that would lead to a decrease in the total precipitation. So on the, these are showing results from various models. On the y-axis is the temperature change, and the x-axis, the total precipitation change in percentage. The points in the top right are from quadrupling CO2, so that leads both to a positive temperature change and a positive precipitation change. And then this G1 is a scenario where the warming from quadrupling CO2 is simply compensated for by a reduction in the solar constant, which is a very simplistic way of representing solar geoengineering, but we see similar things when we actually add aerosols in the stratosphere. Yeah. So yeah, if we sort of compensate for all of temperature change, so we have zero temperature change, we end up with some negative precipitation change. So what we also know is that if we, instead of compensating for all of the warming from CO2 with solar geoengineering, we could halve warming from CO2. And that would seemingly moderate changes in almost all of the regions. So this map is showing results where they compare a RCP 8.5 type scenario. So that's when we add a lot of greenhouse gases to the atmosphere, and a Glenn's type simulation where the global mean temperature, equator to pole, and hemispheric difference in temperature are kept at 2020 levels with RCP 8.5 emissions. And in this paper, they sort of interpolate between these two climates to find the to sort of approximate what would happen if we halved the warming from greenhouse gases using solar geoengineering. And then they show for all these different regions whether these 4 climate metrics are exacerbated or moderated using solar geoengineering. So the 4 climate metrics are surface air temperature, max annual temperature, precipitation minus evaporation, and max precipitation. And if it's in blue, the change is moderated by using solar geoengineering. If it's in red, it's exacerbated. And so as you can see, there are only a few regions where the precipitation minus evaporation is exacerbated in the scenario where we use solar geoengineering to reduce warming, but not compensate for all of the warming. The other thing we have learned is that we could optimize our stratospheric aerosol injection deployment because the climate impact of stratospheric aerosol injection is dependent on how we do it. And so this early study with CESM showed that by using 4 different injection locations and an algorithm to decide how much to inject at each location, we can maintain the global mean temperature, equator to pole temperature gradient, and hemispheric difference in temperature. So then you would avoid having, so in the cases where you just reduce the solar constant, you end up with overcooling in the tropics and warming in the poles. So you avoid that by having these 4 different locations for injection, and also by reducing the hemispheric difference in temperature, or making sure the hemispheric difference in temperature stays the same. You avoid changes in the shifts in the ITCZ, and hence changes in the tropical precipitation. So on the left, I'm showing the results from these simulations, where it's just showing the surface temperature change for each latitude with respect to time. And so in RCP 8.5, obviously the Earth is warming, and it's warming more at the poles. But in this feedback simulation, where you can use this algorithm to inject aerosols at these 4 different locations, you can maintain global mean surface temperature, equator to pole difference, and hemispheric difference in temperature. So that's what we know from sort of climate modeling of stratospheric aerosol injection. And so today I will present a new set of simulations using 2 different models so far. So we have CESM2, which is the one from the group in Cornell, and UKSM1, which is what we're doing here in Exeter in the Met Office. So the experimental protocol is to use SSP 245 because it's thought to be a more realistic emission pathway compared to RCP 8.5, which is probably a bit too strong. And the temperature is maintained to 1.5 degrees above pre-industrial levels. And again, we pick 4 injection locations and use an algorithm to keep the global mean temperature, the hemispheric difference, and equator to pole temperature gradient to their 2020-2030 average. And so each year, the climate is compared to these 3 targets, and the injections are adjusted by the algorithm. So for example, if it's found in one year that the Northern Hemisphere is a bit too warm compared to the target, then the algorithm will increase the injection at 15 and or 13 north. Obviously, it's a bit more complicated than that because we have to account for natural variability. So you wouldn't sort of react every year, but that's more or less how the algorithm works. And so the objective of what I'll present is just to compare the climate impacts of this scenario between CSM2 and UKSM1, and also discuss the performance of the algorithm. So here I'm showing the different temperature targets. So on the left, we have UKSM, and on the right is CESM. And in red, it's the baseline scenario. So that's SSP 245. And in blue is the arise scenario. So that's where we inject aerosols to keep the temperature at 1.5 degrees above pre-industrial. So then on the top, I have a global mean temperature, in the middle, inter-hemispheric temperature gradient, and then bottom, equator to pole temperature gradient. So obviously in red, the temperature goes up because that's the SSP 245 scenario. Obviously the two different models have two different sensitivities to just greenhouse gases. So in the UKSM, we reach about 3.5 degrees warming in 2070, whereas in CSM, it's roughly 2.5. The big picture is that we managed to reach these targets both for UKSM and CSM. So the algorithm is successful at keeping temperature to 1.5. For CSM, the inter-hemispheric and equator to pole temperature gradients don't actually increase that much in the SSP 245 scenario. So it's not very difficult for the algorithm to also maintain these targets because they don't deviate that much from the target in the baseline scenario anyway. That is not the case for UKSM. So the algorithm is successful at keeping the inter-hemispheric temperature gradient to its target, more or less. But it's less successful at reaching the equator to pole temperature target. And so as I'll show, that leads to problems in how the algorithm functions. So here I'm showing the injection rates that are chosen by the algorithm to maintain these different temperature targets. So on the left is CSM, where you have a nice linear increase in each of the 4 injection locations. So in black is the total injection, and then the different colors are the different locations shown here. In UKSM, we have after 2050 an increase in 15 North that makes it look a bit weird, and it's not as sort of nice and linear as it is in CSM. So I spent a lot of time trying to figure out why the algorithm is doing that. I think we finally figured out that it's caused by not being able to reach that equator to pole temperature target, and also a quirk of the algorithm that I'm trying to fix now, but it takes a long time for these runs to function. So it takes me a while to verify that whether the quirk in the algorithm can fix this issue. But regardless, the temperature targets are more or less achieved even with this quirk in the algorithm. Also, for reference, so we're looking at injecting roughly from 10 to 20 teragrams of SO2. For reference, Pinatubo was between 14 and 23 teragrams of SO2. So Pinatubo was a volcanic eruption in 1991 that led to a decrease in temperature for a couple of years. And current tropospheric emissions of SO2 are roughly 100 teragrams per year. So then I'm showing the increase in SO4. So on the left is UKSM, and on the right is CSM, and then also the injection locations in the diamonds. So interestingly, the injection rate for CSM is roughly half that of UKSM, or a bit more than that, but roughly half. Even though the actual amount of SO4 in the stratosphere is more or less the same. So that is consistent with the fact that the lifetime of sulfate in the stratosphere in CSM is about twice that of UKSM. So basically, you can put half the stuff in CSM and it'll stay there for twice as long. So at the end, the concentration of stuff you have in the stratosphere is more or less the same. So then looking at climate impacts, so showing here the difference between the last 20 years of the simulation and the first 20 years in UKSM and CSM for SSP 245. So obviously there's warming more or less everywhere, and the Arctic is warming more, and the land is warming more than the rest of the planet. And then in the ARISE simulations, where we inject aerosols in the stratosphere, we end up with less warming and even cooling in some parts of the world for both models. Then we can look at impacts on the global precipitation. So this is a very simple metric of looking at global mean precipitation. It turns out that for both models, almost you end up with less precipitation at the end of the simulation than at the beginning, although that's less true for CSM. But maybe it's a bit difficult to infer climate impacts by looking at global mean precipitation. So we can look at maps of precipitation change. So again, this is the difference between the last 20 years of simulation and the first 20 years for SSP 245, and then a rise. So I found it, so this is the annual mean precipitation, and I found it hard to really sort of look at this and understand how impactful these changes in precipitation would be. So I then sort of focused on two different areas where it seems like there were large changes in precipitation over land. So that is Central Africa and Eastern South Asia. So on the left, I'm plotting the June, July, August precipitation for both of these areas. So yeah, on this one is the annual mean, and this one is June, July, August. So the colors look more stark because the reduction happens in June, July, August. So it looks like there's roughly a 1 millimeter per day reduction in precipitation over this area, over both of these areas in June, July, and August. So then I decided to plot the seasonality of precipitation over those areas. So on the left for UKESM, on the right for CSM, and the black is the first year of the simulation. The blue is the 2050 of the geoengineered climate, and red is 2070 of the geoengineered climate. And there is a clear reduction in Central Africa for UKESM. There is also a reduction in CSM, but it's less stark. And then in South Asia, there's also a reduction in June, July, August for UKESM, but not so for CSM. So that could be due to this quirk in the algorithm that increased the precipitation in 15 North, which could have led to a shift in the ITCZ, and then these changes in precipitation in tropical land areas. So that I have yet to sort of fully investigate that. Yeah, so then I looked at the potential for perceived failure of stratospheric aerosol injection. So that is a recent paper that was published in PNAS, where they analyzed CESM results, and they found that because of large natural variability, you could end up in the first decade of stratospheric aerosol injection, ending up with a perceived failure because some areas of the world are still warming. So here I'm showing the ensemble mean trend so yeah, just to clarify, in each of these scenarios, there are 10 ensemble members for CSM and 5 ensemble members for UKSM. So that way we can sort of quantify the natural variability that's happening. So on the left, I'm showing the temperature trend over the 20 years before geoengineering. So obviously it's warming everywhere. And then the temperature trend in the 30 years or so after geoengineering started. So they're showing some modest cooling or roughly sort of no temperature change. But that's for the ensemble mean. If you look at these trends for individual ensemble members, and in this case, looking at the first decade before geoengineering starts, and then the first decade after geoengineering starts, you have cases where for certain members, you have large parts of the world that are cooling in the decade before deployment and that are warming in the decade after deployment. So that is why these people are talking about potential for perceived failure of stratospheric aerosol injection deployment. So I did the same thing with UKSM. So obviously, because the climate is more sensitive to greenhouse gases in UKSM, we overshoot our 1.5 degree target, and the temperature trend are starker in the decades before deployment. And there's actually some cooling after deployment because we have to return to our 1.5 degree target. So the ensemble mean trends are larger. But again, if you look at individual ensemble members, you have, some cases where, it's cooling in the decade before deployment, and then it's warming in the decade after deployment. So still, this potential perceived failure is still true, but maybe less so in UKSM because it's more sensitive to greenhouse gases. and there's more cooling required to reach that target. So to be more rigorous, you can count the number of ensemble members that have warming above a certain threshold in the first decade of deployment, which would give you an indication of the potential for perceived failure. So in white, so basically if the color is white, there's a 50% chance, or 50% of the ensemble members have a warming trend in the first decade after deployment. So for CSM, because again, it's less sensitive, so there's less cooling required, yeah, more of the area of the planet is covered in white. It's less the case for UKSM because we have to, there's actually a large amount of cooling in the first decade that happens. So the obvious point is more cooling will reduce the potential for perceived failure. But I guess that is quite an obvious point. Yeah. Okay, so that's more or less it. So I want to mention what next in terms of what I would like to do and what I think we should do in terms of research in solar geoengineering. So in order to reduce the uncertainty in the climate impacts, we need more models to perform the same experiment. And because the algorithm is quite complicated to implement, we're looking at simpler injection strategies. So that's already been done by the group in Cornell with CSM. So the sort of scenario I was talking about is the purple one here, where we're looking at multiple objectives, at satisfying multiple temperature objectives. But they compared it to scenarios where they just use equatorial injection in orange, and then only 2 injection locations in these 3 cases here. And using these either equatorial injection or these 2 location injections, they're only looking at satisfying global mean temperature. And yet, even if they, they were just focusing on global mean temperature, the climate outcome was actually not that different from the multi-objective scenario, where they're looking to satisfy these 3 temperature targets. So if you look at, obviously, the purple one, which is the multi-objective one, is better. But if you compare it to the 30 north and 30 south injection, which is in green, you actually get results that are not too far off the multi-objective one. So it could be that we could use, only injection of 30 north and 30 south and get, a much simpler implementation strategy, and climate impacts are quite similar to the multi-objective one. So that would encourage more models to get on board and do these simulations to then we could reduce our uncertainty in the climate impacts of such interventions. And then on the other end of the spectrum, we'd like to understand how large the design space is. So how accurately and how far can we go in terms of tailoring the climate impacts of stratospheric aerosol injection. So obviously, again, the Cornell group has already done this with CSM. We're just trying to play catch up with the Cornell group, basically. And they found that for a cooling level of 1 to 1.5 degrees Celsius, there are likely between 6 and 8 meaningfully independent degrees of freedom, meaning that you can inject at different locations, different heights, and different seasons to yield a detectably different surface climate response. So that is something that I would also quite like to look at using UKSM. And finally, there's a lot that can be explored using the existing climate simulation ensembles, even though, as I discussed, they're not perfect. They do, we do satisfy the temperature targets more or less. And so we can look at a lot of these climate impacts, for example, impact on monsoons, which is something that I'd quite like to look at. So if you are interested in working on this and analyzing some simulation data, please reach out. I'd be very happy to find a way to get you access to this data, and then we can do some science together. Okay, thank you very much, and I'd be happy to take any questions.
Okay, let's thank the speaker.